Welcome, ladies and gentlemen. This is video number 8 for our bonding unit. This video is going to be on molecular shapes. What are some shapes that molecules can make? And you're going to need your notes open to page 48 in your notes. So shapes of molecules are based on something called VSEPR theory. That's how we pronounce this acronym of VSEPR, VSEPR theory. And VSEPR theory, the acronym means valence shell electron pair repulsion. So VSEPR, valence shell electron pair repulsion. And this is a good name in chemistry because it tells you exactly what's going on. Names that are descriptive are very good things. So this means, if you break this down, valence shell electrons, so we're talking about electrons in the outermost shell, electron pairs, repulsion. They repel one another, right? That should make sense because electrons are all negatively charged. So the electrons in the outermost shell, they repel one another. Well, duh, of course they do. And this includes electrons that are involved in bonds. So this isn't just saying that electrons in an atom will repel one another, but electrons that are involved in bonds will also repel one another. And what this means is that in three-dimensional space, molecules will actually start to take on shapes so that the bonds will be as far apart from one another in 3D as they can possibly get, because the electrons in the bonds repel one another. So we have these different shapes that come from the bonds actually wanting to be as far apart as they possibly can be. The four shapes that we are going to be discussing, these are the four names. Linear, tetrahedral, pyramidal. Pyramidal, notice how that's pronounced. I don't want to hear any pyramidal in class. It's pronounced pyramidal. So really lay on your Western New York nasal accent and give me a nice nasal A, pyramidal. And then there you go, you got the name right. And bent. There are more shapes than this. There are actually many, many shapes, but these are the ones that we're going to discuss. These are sort of the big ones. So first up is a linear shape. Well, this is a great name because it tells you, it's very descriptive about the shape. And notice that we have three atoms here. So we have our central atom, and we have two bonds. And in order to be as far apart from one another as they possibly can, the two bonds are going to be 180 degrees away from one another. So that bond angle is quite literally the angle between the two bonds. And the farthest you can get that is 180 degrees. So this is a linear shape. I think it makes a lot of sense. The three atoms, they're in a straight line. When is this a polar molecule? So this shape can be a polar molecule if the two different atoms that are on each end are different. So if you have the two of the same atoms on each end, like if you have two H's on each end or two oxygens on each end, then this would be considered nonpolar. But if one end is different from the other, meaning if one atom is maybe F and the other is H on each end, again, notice I'm talking about the end because symmetry, we're talking about symmetry around the central atom, then it would be a polar molecule. Our next shape is our tetrahedral shape. Now this is the shape now that we have, notice we have four bonds. And the prefix tetra does actually mean four. So we have the four bonds, the four atoms that are on the outside, they're actually arranged in the shape of something called a tetrahedron. And in three-dimensional space, this is actually the farthest apart that you can make four things. Now you might be saying, well, what if I just do a 90 degrees thing? Like if I'm in math class and I have a XY coordinate axis and I go, up, down, left, right. Yes, 90 degrees is as far apart as you can get four things in 2D space, but we're not talking in two-dimensional space here. Atoms and molecules exist in three-dimensional space. So in three-dimensional space, a tetrahedron now is actually as far apart as you can get because it's a bond angle now of greater than 90 degrees. The bond angle is actually a little bit funky. It's 109.5 degrees. So again, that would be here to here. That's our bond angle. That's the 109.5 degrees. And notice that this guy, he's actually going back into the screen. He's not lining up. And this guy, he's actually sort of coming forward out of the screen. So this is a two-dimensional representation of a three-dimensional shape. So we'll be looking at these in class, 3D, what does it actually look like? When is this molecule polar? So this molecule will be asymmetrical if the four atoms that are bonded on the edges, so this, and this, if they're not the same, if one of them is different, if two of them are different, it will be nonpolar if all four are the same, because then it would be symmetrical. Then it would be all the same all the way around. But if one of them is different, or if two of them are different, then we're going to have a polar molecule. Next up is our pyramidal shape. So now we have A central atom that's attached to 3 atoms, but we also have a lone pair that's on our central atom, right? So we have 1, 2, 3, but then our lone pair. That's what this bubble is. It looks like a pyramid, which is why it's called pyramidal, because the central atom would be the top of the pyramid, and then the pyramid would have 3 sides. This shape is actually related to the tetrahedral shape. The bond angle, though, is less than 109.5. Now, the reason I just say less than and I don't give you an actual number is it can vary from pyramidal molecule to pyramidal molecule, but we mean it's slightly less. And slightly less doesn't mean crazy less. So maybe instead of 109.5, it would be like 108.5 or 108.2, something like that. So it's a little bit less. It's not crazy. It's not like 82 degrees. It would be a little less than 109.5. Now, the reason that it's less than is actually the lone pair. It pushes down. It provides more repulsion. It pushes the other atoms away. So these guys actually get a little bit closer because that lone pair is repelling a little bit more. When is this molecule polar? Well, here's the thing. This molecule, this shape, is always going to be polar because the lone pair on the central atom is always going to make it asymmetrical. A lone pair versus a bond, those are 2 different things. That is asymmetry right there, my friend. This shape will always be polar. There is no way that you can have this shape be nonpolar, because that lone pair, which makes it this shape, will always be there, and that will always be different from the bond. It will always be providing an asymmetry. Next up is bent. This is water. Water is the classic example of a molecule that has this bent shape. So now in a bent shape, we have a central atom that's attached to 2 atoms, so we have 2 bonds. But our central atom also has 2 lone pairs, right? So these are our 2 lone pairs. And then our 2 bonds, right down here. 2 bonds to 2 other things. And now the bond angle is much less than 109.5, but when we say that, we don't mean crazy. We mean like maybe 105 degrees, 104.7 degrees. But it provides more repulsion because now we have 2 lone pairs. So these guys, that's the bond angle, the angle between the 2 bonds, they get even closer than you would expect them to. When is this shape polar? Well, this is exactly like the pyramidal shape in that this shape will always be polar because the lone pairs on the central atom will always be different from the things that the central atom is bonded to, right? Lone pair versus a bond, those are 2 different things. Polar means asymmetrical. Polar means different. So the lone pair on the central atom will always, always, always make it different. We're going to work more in shapes, but with shapes in class, and we're going to practice with this so that you feel comfortable identifying shapes and polarity.